Okay, class, today we'll look at chapter 8 to study structure, vibration, and dynamics. We'll use ANSYS to work on example, which is guitar. We will look at its natural frequency and also look at its response to a harmonic input. Okay, look at the figure here is geometry of the guitar. We'll start with 2D and then use the point listed here. The coordinate of the point has been given to draw a 2D shape of the guitar and then draw up and pull up into 3D. Material given is Douglas fir. Boundary condition we applied is back face is fixed and the harmonic pressure 1 megapascal will applied on the side wall. So that will be used for frequency analysis. Recall that frequency analysis is given a harmonic input, sinusoidal stimulus, and to look at its response. Okay, so again, the first task is to do a modal analysis, which is find the natural frequency of the guitar system. Okay, with this information in mind, we'll go into Workbench to look at how to use Workbench to create this project. Okay, the project we'll work on is a modal analysis. So this time we'll use Modal to create a new project where we'll start from the material. The material we'll name it as Douglas fir. Okay, so after that we define this material property. We start from the elasticity. Isotropic elasticity will be used. Input is Young's modulus 13.1. GPA Young's modulus, let's use 0.3 as is Young's modulus. After that, we'll another parameter we need is needed for modal analysis. That is the density. Because think about if we want to know the frequency of material, and then its density is necessary. So click on Douglas fir, go to the toolbox panel, and the physical property, find the density. Double click on it, and then input the density of Douglas fir, which is 470 kilogram per cubic meter. Enter. Okay, and then we close engineering data. We move on to geometry. For this problem, we'll make sure that the surface body will be used because we will use a shell structure. 3D type. Make sure 3D has been selected. So after that, we'll double-click geometry, launch the space claim. The first thing we'll do in space claim is we'll set the unit. So go to File, Space Claim option. Units. The units we'll use is millimeters. Primary precision 2 is okay, and then we'll change this minor gauge to 10 because the smallest length will be used as 10 millimeter. And click OK. Then click Z. Oh yeah, first select a new sketch plane and then click Z, which will lead to XY plane. Go to the design, click a plan view. So we'll in the 2D plane, and here we'll draw the 2D guitar shape. So we start from drawing, put all the point on this 2D plane. So what we'll do is we'll click on point. Here we'll put point on it. So we'll need Cartesian dimensions to help us to locate the point. So the first one is as a center of origin, so just find the center of the origin and then click on it. And you will see that the first point has been created. And you can use the structure panel to track the points, the number of points you have created. The second point is B with coordinate x0, y10. So I will use Cartesian dimension, start from origin, and 0, 10. Second point has been created. Escape. I try to zoom out a little bit. And then move it down. Okay. We'll continue to the third point, 30, 70. Use Cartesian dimension. We'll go to 30, 70. Okay, third point. D is 60, 80. We'll go to 60, 80. Start from origin, 60, 80. Let's go up, 80, 60, 80. Okay, confirmed. Click, escape. Next point, 170. 170. 170. Confirm. Click. Next point, 140, 50. 140, 50. 140, 50. Okay, confirmed. Click. Skip. Next point, 260. 260. 260. So make sure that is 260. Okay, double check. It's right. Click. Confirm. $260. Sure this is right. Next one is 220, 50. 220, 50. 220, 50. Click. Confirm. Then 240, 10. 240, 10. Then 240, 0. The last point will be in the middle of the guitar, where we'll dig a hole into the guitar, which located 170. Click. Alright, and then we have all the data which will be used to plot the 2D. To draw this 2D shape, we'll use Spline Structure function. So click on Spline and start from origin, second point, third, and then go all the way to the point. Okay, so now we have the spline that constructed the upper half. So we'll use mirror function, go to mirror, and then click on X, which will be our mirror, and then click on spline we created, which will generate the second half, the bottom half spline. So let's move it out. Now we have this enclosed area 2D shape of the guitar, and we'll pull it up by using pull function. You could click pull, and the surface will be created. We'll use this surface to pull it up. So we'll rotate it a little bit to make sure that it's in a 3D mode. Okay, so we'll pull up along Z direction by 50. So input 50, enter. Okay, so now we get this structure, and the next step is we'll dig a hole into it. So to do that, we first use select this surface where the dot located at here. So make sure that you choose this selection, this surface, and then we'll use this dot to help dig a hole here. And then when I select, click on this circle drawing. So you'll see that the sketching surface will be created along this surface, where we'll use this dot at the center, create a hole which is 45 diameter, and then escape, and then click Pull, where we'll use this to cut into the solid. So where we can put a number, let's use 10. So this geometry doesn't matter because eventually we will create a shell. So inside the solid should be hollow, but the thickness of the shell will be 3 millimeters. So any number larger than 3 millimeters will be good. Right? Now we have this structure. Again, this is a solid material. This is not a shell yet. So to create a shell, and then we will use the shell button here. Create under the design tab. Click on shell. After click on shell, and you will see that when you click on any surface, it will remove the surface from the shell creation. So that means, and this part, this part is, we will remove it. So this part will not join the shell creation. So we'll remove this part, the bottom of the small cylinder we created. So you click on it, and you will see that that part will be moved, and a shell structure has been created. And here, and you need input the thickness of the shell. I input 3 millimeters, and the 3 millimeter shell has been created. Again, that's not the end, because we don't want this, the side wall of the small cylinder either. So we want to remove too. So we can continue click on it. It will also remove this part from the shell structure. So make sure that the side wall is selected and click on it. So once we finish this and click move here, click the check, that means complete the shell creation. Alright, and then the shell has been created. We'll put the shell into a surface, and then the next step is we'll do, let's see, where is it? Oh, prepare. We'll go to prepare. We'll put a mid surface into the shell and click on the mid shell. When you click it, if you move down here, it will show you that you need to select the surfaces to create the mid surface, and I will use a range, and the range is with maximum thickness larger than 3. If you larger than 3, because the shell we created is 3. If the larger than 3, when we click on this shell, the ANSYS will know that this shell will be used to create the mid surface. And then click check, complete, and the mid surface has been created, and the mid surface will have 3 millimeter thickness. Well, meanwhile the solid part has been silenced or suppressed. Okay, with all of them set up, and then we'll go to next step. Control S, I will save this structure, name it design 5. Okay, close it. Double click on Modal. Okay, it's loading the structure. Okay, here we are, and we go to geometry, select smooth surface, and assign material to it. And the details of the made surface, we'll choose Douglas fir, which is the material we have created. And then move to mesh. Here we will insert a mesh. Click on size, sizing. So first we need to choose the surface we'll want to mesh, and we'll choose all the surfaces. So Control select. Make sure the 4 surfaces have been selected, and then apply. Mesh size, here we'll use say 0.005. After that, right click on mesh, generate mesh. Okay, so here we have meshed the guitar, and you'll see that the mesh is fine enough, so which is good. And after that, we'll go to a model to set up boundary condition. The boundary condition we'll use for the model analysis. So we'll fix the bottom surface. See, the surface filter has been enabled, so select this bottom surface and then apply it. The boundary condition has been applied. So click on analysis setting, enter model, and the maximum modes to find, we can go up all the way to 10. So you can change the number, but what really matters is the first few modes, the natural frequency of the system. And then at last we will insert the output. I will insert total deformation, total, and here you will see that this total deformation by default will set to the first mode, so the lowest natural frequency. And then we can continue to input more deformation, and this will be for the second mode. It depends how many modes you want to show. Third mode. The higher more mode you input, that means the higher frequency you want we want to seek. Okay, now all that has been successfully set, and then we solve the problem. Okay, so all the results have been successfully obtained. So if you click on the first total deformation, which is for the first mode, the first mode has natural frequency is 1083.2 Hz. The deformation, how it vibrates, is shown in this way. This is how it vibrates. Okay, so second mode, the frequency will increase, and well, the deformation will look like this here. Third mode, fourth mode, and fifth mode. Okay, and that finished our natural frequency study. Well, you can see that is on this figure. You can see there's you can see the animation of this vibration, how it vibrates. And this figure will show you that where this we have 10 modes showing up here too. Okay, the tabular data shows the frequencies. Okay, so we've accomplished the first task, and then I will close this. We'll work on the second part, close the mechanical model analysis, and we'll work on the frequency analysis. The frequency analysis we need use harmonic response project. So, but we'll not start from the beginning, and we'll based on the modal analysis. So we pull the harmonic response to the solution of the modal project analysis. So move harmonic response, drag it to 6 solution, and then release, which will generate a harmonic response based on the modal analysis result. So, and then click on setup here. So click on setup, double click on setup, which will lead to the mechanical model again, but this time we'll do a harmonic response based on the result of the modal analysis we have performed. And when we come to this part, you'll see that we have a modal analysis and we have harmonic response here that waiting for us to sign the boundary condition. So the boundary condition we'll apply pressure on one side. So because the symmetrical structure, we can side on either side, or side on the side wall. So make sure that the face has been selected, and then select the face here, then apply, and then we'll apply a pressure on it. The magnitude of pressure is 10 to 6, so 1 ampere. Okay, and then the frequency will assign us. We'll start from 1000, because we know that the first mode is 1083. So the minimum range, the lower ranges should be smaller than that, and the higher range, we know the 10 mode, the largest mode, is less than 4000. So, and then maximum frequency we'll apply is 400 Hertz. And the interval we'll use 300. So that means we apply pressure, which is harmonic pressure, means with some frequency, and the frequency will start from 1000, and then after one calculation, it will move to 1300 Hertz and keep going up until that to the upper boundary 4000. Okay, so that's the boundary condition. After that, we will insert the output. The output will use insert frequency response. We'll look at its deformation. Okay, so we can look at its deformation, and we'll look at the deformation because most of the deformation come from this the top surface. I'll click on top surface and apply. And the deformation is mainly mainly about z direction. So this orientation, I will use z axis. So look at the z axis deformation. Okay, and then we can solve. Alright, we finished the frequency response analysis, and if you click on frequency response, you'll see that this is typical frequency response result to show you that when we change the frequency of the stimulus, and the response also follow a sinusoidal form, but its magnitude, amplitude of the response will change. So, and there will be a phase angle, and there's the input and the output. There will be a phase lag. Well, it showed up here, and then that you will see that at natural frequency, the amplitude achieves the maximum value, because the resonance phenomena, when you at the maximum frequency, at the natural frequency, you have the maximum vibration. Okay, and shows there will be 10 mode, and this small region there's a zoom in region show the rest of the mode. Okay, so that's all we have for this project, and we'll stop here.